Welcome to the NPTEL course on storage systems. Last time we were starting to look at some specific systems. I believe I came up to this point. I was talking about the file system that exists in Linux, and basically we are talking about some way of locating the blocks on the file. And what we were talking last time was that the size of the file can be varying from small to very large. For example, you can have some files are exactly 0 bytes, 1 byte, all the way to terabytes. Okay. So, you should be able to scale to all these levels, and it turns out that this scaling is achieved in these kind of systems through multiple pointers, okay, through a structure like this, where there are direct blocks, indirect blocks and double indirect blocks, and there are some systems which also have triple indirect blocks, so that you can even go higher. Okay. Now, think about this particular file system. It is a kernel based file system. It is in the kernel. Okay. That is, it is not outside, it is not in user space. Okay. That means that these kind of systems are very difficult to engineer, change, okay, and typically these are modified only with great care, okay, because kernel code is extremely difficult to engineer to get it right. So, therefore, we find that there is newer versions of file systems, but that happen every so often. For example, we had ext2fs. This came in 1992 approximately, or 93, somewhere about that time. Then we had ext3 about early 2000, I think. Then about 2005 or 6, they were designed for ext4, which is what is being used right now. Okay. So, and now there is something called BTRFS, which is now also being looked at. Okay. These things happen every few years. Okay. The next one which I am talking about is a what you might call as a user based file system. This is the Google file system. Okay. Now, what we are talking about here is a system that uses information stored on this side and being accessed through an application. Okay. Now, it turns out the Google file system is a user level file system, means it is not in the kernel, it is outside the kernel, and actually it uses a Linux file system as its base file system. So, all these file chunks are actually stored in the Linux file system. A file chunk in Google file system is 64 megabytes, okay. It's a huge one, 64 megabytes. Okay. So, it has files much bigger than that. So, just like a block, here for example, you had a notion of a block. A typical block in this kind of systems is about 4 kilobytes. Okay. Here in Google file system, something like a block, I shouldn't call it block, they call it a different name, that is why it is called a chunk. What looks like a block in Google file system is a 64 megabyte chunk. It is a huge big piece of thing, and this has been decided because you want to optimize on the performance of the disk based system. This is basically a disk based system, okay, with respect to the storage of information. Okay. Why is that? Think about it. If I am in a disk based system, every time I want to access something, I have to first do what is called seeking to a particular place on the system, on the disk, on the platter, and then later I have to wait for the head to come below the place where the information is stored. Okay. Now, that is why there is two aspects to it. One is what is called the seek time, and then there is something called the rotation time. These two things are not easy to decrease, because it is an electromechanical system. It has been for quite some time between 30 milliseconds, nowadays you can get up till about 10 milliseconds. So, since the last 20-30 years, it has decreased only from 30 to 20 milliseconds to 10 or 8 milliseconds, the combined aspect, combined both these things. And that means that the progress in this is very slow compared to the other amazing progress you see in other areas like CPUs, disk capacity. Those things are doubling, increasing at almost twice every year. okay, or something in that region. Okay. Whereas because the disk being electromechanical, you are not able to make such amazing advances there. So, one aspect of disk technology is that it is fundamentally slow. That means, if I want to seek someplace, I need 10 milliseconds. Now, just imagine the following situation. I want to read one block 4 kilobytes at one place, and then I want to move to another place. Okay. So, let us look at okay. Some
the desktop.
Desktop. Here? No, not here. Forgot where it was.
First one, sir. First program. Window channel.
Okay. Okay. So, see, if you think about it, you have a. Okay, sorry. Let's say it's a disk. You have a block here, and you want to move to this block. Okay. So, this could be on one track, this could be another track. So, that means that I have to first move from this track to this track. So, there is a track seek time, okay, followed by I have to move my head from here to it was somewhere here, right, and it has to move this much, okay, the distance. So, there is also a rotational aspect. Now, track 6 of, let us say, we will just conservatively assume to it 10 milliseconds. Rotational aspect, full rotation, let us say, is 10 milliseconds. Typically, we will do about half, so it is 5 milliseconds. So, 15 milliseconds total. Now, if you are talking about 4 kilobyte blocks, right, what does it mean? It means that for every 4 kilobytes, you have a cost of 15 milliseconds. Okay. Now, how much is the time taken for 4 kilobytes? Typical disks nowadays, you can do about, let us just say, be conservative, we will say 100 megabyte per second. Okay. This is typical bandwidth. So, if you take 100 megabyte per second bandwidth, how much will 4 kilobyte take? So, you can easily see that it is about 100 kilobytes for millisecond. Okay. So, we are talking about 4 kilobytes in 1/25th of a millisecond. So, what we are doing is we are saying that if I want to go from here to here, I have an overhead of 15 milliseconds, but actual transfer time is 1/25th millisecond. This is totally off. Okay. It makes no sense, but that is how systems are built right now. Okay. That is the reason why there is a lot of emphasis on all file systems to bunch things together, to make things as, let us say, clustered as possible. Clustering. You want to cluster the blocks. It's very critical. Okay. So, you can see the difference 15 milliseconds, 1/25th millisecond. These are useful activity, this is overhead. Okay. We are talking about a utilization of barely less than 1% if you do a seek every time. So, a critical thing about a disk is that if you want to really get any performance, you have to avoid seeks as much as possible. You should be able to do about 10, 20, 30 blocks sequentially before you again do a seek on. Okay. Now, this has been carried to much bigger levels in the Google file systems. There is 64 megabytes. Now, just see what is 64 megabytes. You can see it is approximately about half a second, slightly more than half a second. So, we are talking about half a second, which is about 500 milliseconds of data time versus 15 milliseconds overhead. Okay. That means that they have to do one critical thing. What should the Google file system do? They should put lot of things together in one place. In 64 megabytes, they have to put lots of things in it. Okay. So, when you are doing search, okay, they have all kinds of information about various web pages. They are going to put all those web pages and put them into 64 megabyte chunks, because they are talking about a very big system, some hundreds of petabytes or tens of petabytes. So, for them, they have that information, they try to pack it in, and there is some other infrastructure which you have to build on top of it, which will locate those web pages within that 64 megabyte chunk, and that is being done by some other system. The file system gives you the ability to pull it out from the disk and write it back, etc. But there has to be another system which actually looks into finer, let us say, granularities inside these 64 megabyte chunks. Okay. and that is what is called bit table, which is, I think we will come to that also later. Okay. So, there are two systems in operation. Okay. Now, so basically these things are 64 megabyte chunks, and they are basically being served through chunk server. That means that this is a Linux file system here. Chunk server is a server on the Linux system which knows about the locations of these chunks. Okay. So, there is one Linux system here, is probably another Linux system, they are coding all these chunks. Okay. And you notice also something we have written is redundant. Sometimes what happens is the file 1, chunk 1 is also available here also in some other Linux server as another copy. Okay. So, there could be 2 copies or 3 copies, typically 3 copies are kept, so that even if this particular system dies, the other things are available. Okay. The reason why they have to do it is because at the scale at which you are doing it, you will find that failures are very common. Okay. So, what you should do is you should design a system which is somewhat tolerant to failure. That is a critical aspect of the system. Again, why is that the case? It is because if you, again let us think about that part again. Okay. So, normally it turns out you can, a disk has got a bit error rate of 10 to the power of minus 15. What is it? 10 to the power of minus 15 bit error rate. That means that if you, in spite of all the coding that is done, Reed-Solomon coding, all the sophisticated error coding techniques are used, in spite of that, there is a residual error that is always there, that is 10 to the power of minus 15 bit error rate. What does it mean? It means you have 10 to the power of 15 bits, you will have 1 bit wrong, 1 bit is gone, whatever you do. Okay. That is what the disk will give you. Okay. The disk specification will give you 10 to the power of minus 15 bit error rate. So, now how much is 10 to the power of 15 bits? It is about 10 to the power of 14 bytes, that is about 100 gigabytes. Sorry, terabytes, made a mistake, this is terabytes, right, 100 terabytes. So, if you are talking about a system which is about tens of petabytes, that means that within that system there are at least about 100 or more bit errors, bit flips, somewhere there, we are not able to figure out. These are bits in error which you cannot figure out, whatever we do we cannot figure out whether they are okay or not, okay, because the disk has no way of finding out. Okay. So, these are somewhat dangerous errors because there is no way to figure out this. So, you have to build some additional things on top of it, okay, and that you can do by having some other extra error coding techniques on top of it. Okay. So, so basically it is not only because of the disks, it is also the case that you will have errors while transmitting it from multiple places, because you have, as mentioned, the servers out here, you are transmitting it through some network, they are going through some memory, right. This memory also can do bit flips. You normally use what is called ECC, this is error correction codes. Okay. Even these ones, their bit error rate is somewhere about 10 to the power of minus 12 or something like that, or minus 13, somewhere in that region. That means that even memory can get corrupted, and there is no way, the ECC also will not be able to tell you that something is wrong with it. Okay. That means that there is a problem here itself. So, there is a problem from the disk side, there is a problem from memory side, there is a problem from the network side. Okay. So, you basically want what is called end-to-end guarantees, end-to-end guarantees. Okay. That means I need to be able to say I am sending something from this side, in spite of whatever is there in between, I should be able to get it intact on the other side. How do you do that? That is a big issue. Okay. So, one way to do it is, in addition to the coding that is done, I should mention that there is coding everywhere now. Memory already does some coding, ECC memory is there. On servers, you almost always use ECC memory. Networking also has some coding. For example, Ethernet is very good, they have very good coding. For example, gigabit Ethernet their error bit rate theoretical is somewhere about 10 to the power minus 20. It's very good. So actually the medium will not do any problems, but when it comes to when you attach two things, okay, sometimes there are problems. Okay, I think some of you know that electrical connections are sometimes not very good, right? Some diodes can be formed sometimes. Okay, if you have studied any electrical engineering, you will notice. Okay, sometimes connections are not made well. Okay, so that's why even though the medium itself is very good, there could be other somewhere else. Okay, when it comes to electrical contact. Okay, similarly, the disks have a problem. Okay, they're all engineered extremely well, so well that most of us don't know that this kind of problems will exist. Okay, for a random laptop, the amount of storage that you have is sufficiently small that probably during the lifetime of the laptop, you might see only 1 or 2 bit flips. That's all. Okay, and that will result in some random hanging of the machine or some crazy thing. Okay, hopefully it doesn't spoil your thesis. Okay, whatever writing. Okay, mostly it doesn't do those kind of things. Basically, because the amount of stuff you write and I write is so small compared to what systems are there. I think last time I talked about it. Even if we spend all our time typing, right, barely you can come to megabytes, right. So what is there on your laptop is mostly other stuff other people have created through programs. Your browser, which is about on my laptop, my browser takes as much as something like 2 gigabytes. I didn't write it, right. But there was a program written and that was collecting all kinds of information as it was browsing things, and it's actually 2 gigabytes. Okay. So even in that larger number like 2 gigabytes, the chances of error are small. Okay. That's why usually it will not hit your critical information, whatever your address, whatever written, etc. Most likely because you're talking about a megabyte kind of thing versus gigabytes. So chances of your hitting that error is 1 in 10 to the power of 3 or less. Okay. So you won't normally see those things. If it hits it, it's going to hit some system program typically. The big browsers, I told you 2 gigabyte Firefox. Okay. So if there is a bug, it will hit that part and it will randomly crash. You must have seen some crashes on your system sometimes. Okay. Of course, you can't blame all these guys for it. It could be software error also. Okay. But normally it attacks those things. Okay. So, so there are errors all through the system. Luckily, they are very small. But the minute you go to large scale systems like Google File Systems, or remember that there's something called CERN, right, where they were trying to find out some new bosons, right, you must have heard about this one. They essentially, I don't remember the exact details, but they collect a petabyte per day or something like that, or 10 petabytes per day, I forgot the exact number. That's the amount of information that comes in. For those guys, that information they're collecting every day will have about at least 100 or 200 or 1000 bits flipped. Okay, they have to do something serious. How do they do it? On top of these things, they try to do this end-to-end guarantee. How do you do it? At the time it is generated, you put one more error coding on top of it. Okay, and then when you get on the other side, somehow you have to make sure that that error code will tell you whether it was transmitted from this side to that side intact. Okay, so a big subject on some of you might be interested in this area, but there is a big area which about coding theory, which will help you to understand these parts. Okay, so you need also a overall coding that happens if you want to give end-to-end guarantees. Okay, now what these guys are doing, Google kind of systems, they are essentially saying that if there are any unrecoverable bit errors, it is being handled through copies. Okay, they are not going to do any coding on top of this. But if you are talking about newer systems, they might also involve coding on top of it. Okay, so these are basically Linux servers. These file chunks are sitting on Linux file systems, most probably ext3 file systems. And application, what is application in the case of Google? It's going to be a search application. Okay, and what it does is it talks to a master. What's a master? Master keeps track of the metadata. Okay, it knows, for example, which chunk server has got which file chunks. Okay, so what happens is that this master has all this information sitting in memory. It doesn't, it's not there in disk. Everything is memory based here, everything. Okay, and it has got a shadow copy just in case something happens to the master. It's a single master system, so this is a single point of failure, but because it's a shadow master, it can kick in if some bad thing happens to this guy. Okay, you don't have a system which has got multiple masters at the same time, because that design is even more complicated. We will talk about those things later. Having multiple masters at the same time is a slightly more difficult design. It has to be handled. Even advanced systems do that part, but in this particular Google file system of 2003, they had only a single master, and they had a shadow master just in case this master failed. It will come in only when the master fails, otherwise it is a passive subject. There are now systems with active masters which can distribute the load also, and this master has a chunk mappings. So when an application wants some details, it asks the master, give me the locations of where these things are. That's what the chunk mappings are. And then application doesn't have to go to the master again, it can directly access the chunks. It knows that from the information it got from the master, it knows that this file chunk which I am interested in is there in chunk server 2, 7 and 8 at this offset, whatever it is. And then it talks to the chunk server. Chunk server is user space program. It goes, talks to the file system, ext3 file system, and says, give me that file which you have stored chunk 1, file 1, etc. So there might be files in the here just saying F1 C1, F1 C2, F2 C1, etc. Some names of that kind. Okay, so the chunk server just give me F1 C2 from ext3 file system, something like that. Okay, and then those things are again sent back to it doesn't go to the master again. So that goes to the master only at the time when it is seeing something for the first time. Okay, otherwise this guy will cache things, etc. Most of the attempt is to make sure that these things are picked up in large sizes, kept in memory, so that you don't have to suffer these 15 millisecond delays. Okay, this seek times, and the master index is completely in memory, so that it's almost instantaneous. The reason why we are able to see so many searches coming out very quick is precisely because most of it is memory based. Okay, so this is an example of a user based file system on top of a base file system. The base file system being Linux system. Okay, this is a different set of constraints compared to the kind of constraints that a kernel based file system will have. Okay, so we will look at some of these things more in detail. I think at this point I just wanted to give you two examples, one a kernel based file system and a user based file system, and the design aspects are quite different. The concurrency, what you want can handle in a kernel is different from the concurrence that is possible in a user based file system. For example, the concurrency here can be depend just on how many chunks are there, whereas in a kernel based file system, you cannot go beyond a certain number of kernel threads because it starts eating up memory. Okay, it becomes slightly more difficult to scale. Okay, this is much more scalable. Okay, so but the scalability is limited by the master size. The master, because everything is in memory, this part of it decides how big the system can be, because everything, all the metadata is stored in memory. So this can have about, let us say in those days beginning, that some you can guess as some approximately hundreds of gigabytes. Okay, in those days, 2003 approximately. Okay, nowadays it will be terabytes of memory. Okay, some people are talking about, even if you talk to high performance computing areas, they will talk about servers with petabytes of memory. Okay, but I just want to mention that there are some scalability issues in every of these designs that will decide exactly how far you can go. Okay, so one thing you should, when you think about all these things, is that there is a deep layering in the system. So as I mentioned already, we have already mentioned that the Google file system is sitting on top of Linux file system. That's one example of layering. But if you think more carefully, it turns out the layering is much more extensive. Okay, for example, there are various types of abstractions in the stack. When I talk about stack, I am talking about the software that is running all these things. Okay, there is a device specific stack, the block specific stack, file specific stack, application level stack. Okay, so for example, a disk can be what is called a SCSI disk. Okay, and it turns out SCSI has itself multiple layers in it. Okay. For example, SCSI has what is called upper layer, mid level and lower level. Now, the reason why it is like this is because SCSI itself is a very generic protocol. Okay. I think you might be aware of this because nowadays you get USB sticks, right. Not only can you use it to store memory, it can be used for networking, right. You must have come across this internet access things which also happen through USB. So, USB is a specific hardware format for interconnection, for not I shouldn't say interconnection, for getting some service. Your camera, for example, has some way in which to interface with USB devices, right. It has got some connector by which it can convert whatever you want to transfer there into USB sockets, right. So, you will see that USB has the ability to interconnect with lots of things, not just storage, it can be the communication, it can be to other things, printers, etc., right. That means that this USB is so, let us call it flexible, it can talk to storage devices, it can talk to network devices, it can talk to printing devices, whatnot. That means that somebody has to make sense of all these things. How is it done? It is done by layering the system, and the layering system first says the lower part of it is strictly connected with sending bit patterns, zeros and ones. Okay. I am just giving you one type of layering that is going on in USB devices. Okay. We will come to that later in more detail, but lower level, the lowest level in that on the stack will be, it will be just communication of bits. On top of it, you need to have some other things. Why? Because when you are, for example, you already put your USB stick on a laptop, right. You want to say I want to write to it, right. When you write to it, there is a speed at which the CPU can give it, the speed at which it can be put into the magnetic medium, if it is magnetic medium, or if it is solid state device, it has got a particular speed at which it can accept it, the information. That means that the CPU cannot just say, I just throw it at you, take it, right, because other party should be willing to accept it at a particular whatever rate it is capable of. Or imagine a printer also, right. Printers, you know that it is slow compared to electronic devices like memory sticks, etc. That means that the CPU also has to slow down with respect to slower devices. Somebody has to do this part. That is sort of a protocol specific thing. They have to talk to each other. One guy is sending bits, but the other guy on the top has to watch and see at what rate it has to be sent. And one can say, I finished writing it, you can now send me this next one. These are all the protocol specific. This is what is called, there is a way in which two guys are communicating. They are talking to each other and saying, yes, I am done, now you send me the next one, okay, or various things of that kind. Or it could also be something like, I am a tape, I can tell the other guy, please do rewind, go to the beginning, right. Somebody has to send this, that also is a protocol specific act, okay. So, it turns out there are device specific things, like for example, tapes, you know, they have some device specific things. There is this protocol specific things, sorry. There are communication layer specific things. USB has similar things, SCSI also has similar things. SCSI is basically a storage protocol, USB is a slightly more general protocol, it is not only geared for storage, but SCSI is very much geared for storage, okay. And we will discuss why SCSI has a certain storage aspect to it. What do you mean by saying a storage specific aspect? Basically what we are talking about, what we mean by that is that you know that storage is slow. When you are dealing with slow devices, you might have a different way of dealing with than if you are dealing with fast devices. A good example is, suppose I want to seek to a place, it is going to take 15 milliseconds, let us say. Now 15 milliseconds you can say is something like, almost like to paraphrase, because what is the unit of time for CPU? It is about nanoseconds. What is the difference between nanoseconds and milliseconds? It is a factor of 10 to the power of 5 or 10 to the power of, approximately 10 to the power of 5. If you think about it, it is like 1 second versus 4 to 5, 6, 8 weeks. Okay. That means that the CPU, when it makes a request, it can take something like such a large time. The best thing is to let the device tell you when it is done. I can't be keeping on checking whether the guy is done or not. I initiate it and then I let that slow device take whatever time it wants to do it. When it's finished, it is its job to tell me that it's done. I will not be polling it. I will not be keeping on checking it, has it done. That means that suppose there's a bus. All these devices are sitting on it, CPU, slow devices, all those guys are sitting on it. Normally, the fast guy is usually the bus master. Okay, that guy decides when you can use it. But in this case of SCSI protocol, because it is so slow, it also can, the slow device also can become bus master, because only it knows when it is done. Otherwise, I have to keep on pulling it. Okay. So, you will notice that there are some specific protocols, device specific aspects in the protocols. Okay. So I just mentioned about block devices. I think we looked at this previous system. This is an example at which there is some protocol between chunk servers, application, master. There is some protocol here also. Okay. Not only at the device level, but there is also at the user level, there is also another protocol going on. Because they are different things, these are all different systems. These are Linux system 1, Linux system 2, Linux system 7, application is running somewhere else, okay, master is somewhere else, all these things are, there is a protocol going on. Okay. Now, what is more interesting also is that you might have heard about the network stack, right? You heard about this 7-layer stack, etc. It turns out storage actually uses, because if you look at it, there is some networking going on here also. That means if you look at the whole thing, not only is there a storage stack, there is also a network stack also as part of your system. And there are very specific network stacks for storage. For example, there is something called fiber channel, which is a storage, which is a stack specifically for transferring large amounts of data. Okay. When doing backup, etc., it turns out that the amount of stuff that you have to send is so huge. Okay. It makes sense to have a specific protocol which is geared for storage only. Okay. So there is, we have in addition to various things, we also have storage. In some sense, our stack can be as many as 10 to 15 layers deep. Okay. If that many you can do it. Okay. The thing which is interesting for us is why storage systems have been a part of the operating system for a long time, has been that a good part of the stack is in the kernel. I think all of you know about the TCP/IP processing happens in the kernel. Some of these file system things here all happen in the kernel, right? So, a good portion of the kernel, good portion of the storage stack is the kernel. Okay. So, but because of the difficulty of working in the kernel and all kinds of new things are happening all the time, people want to have a slightly easier time. Working in the kernel is hard. It's only for real professionals, you might say. So, people are trying to figure out slightly easier ways of doing it. That way is the one way to do it by sitting on top of it, like the Google file system, and this will be done through probably, who knows, Python scripts, whatever. Okay? They can do all kinds of things of this kind here on top of it. Okay. So, there are various languages available now. You can do it through Java, you can do it through Python scripts, whatever. Okay. So, which actually coordinates across these things. So, this is slightly more easier. Okay. The storage stack is migrating out of kernel with separation of processing and storage. This makes it slightly easier. One thing about storage also is that by definition, concurrency, almost by definition, RSS natural. Why is that? Because you are dealing with slow things. When you are dealing with slow things, what is the idea? You let all the slow things, you initiate all the activities in slow devices, and then you do other things, right? So, because you cannot afford to wait for them. If you wait for them, that means you are stuck, you can't do anything useful. So, what is the idea? The idea is basically make sure you have large numbers of things you can initiate in parallel with other things you are doing. right? So, you are waiting for something, you want to do something useful. Okay. So, because of wide disparity in speeds of memory and storage, you have to mask slowness of storage, and the only way to do it is by parallelism, concurrency. Okay. Make processing and storage go at their own rates and use interrupts or sometimes polling to signal completion of slow storage operations. Okay. Actually, interrupts were devised in 1957 for exactly the same reason. The only reason why we have operating systems is because of this difference in speeds. The first interrupt based mechanism was invented by Dijkstra in 1957. That is why he actually started as an operating system guy. Okay. And finally moved off from operating system to theory of concurrency, how to write programs, because once you have concurrency, it turns out very difficult to reason about it. Operating system is all about reasoning about concurrency, good part of operating systems. Whole of concurrency theory comes from this issue about matching disparate in speeds of memory and storage. Okay. So, this is a historic reason why operating system developed, okay. Basically because of this part. If everything is working extremely fast, there is no need for you to let us say think about concurrency that much. Okay. Only one because something that is so disparate, then you have to do something serious. Okay. The other thing about, so one is concurrency is important. That means that your file systems, for example, are engineered extremely carefully so that you are as concurrent as possible. Because you are trying to be as concurrent as possible, it is very difficult to get the programs working right. Okay. So, that is the reason why people do not usually write file systems from scratch. Typically, they want to avoid it as far as possible, because it is very difficult to debug it. Okay. The reason why it is even more difficult is because if you want to debug it, you have to be your own guinea pig. It has to work for you before you can tell other people to use it. And when you are debugging it, it will be harrowing experience. Nothing will work. Okay. So, that is one of the reasons why file systems and storage systems change slowly. They do not change very fast, because you have to guarantee that the data you write is actually there. When you want to access it, it should be there. If you are not able to guarantee even that minimal thing, it looks like a small thing, but actually it is a very tough thing. You can't even get started, because you are going to store your, if you are developing the system, you have to depend on it, you have to use it yourself. Okay. As I say, there is a famous word in, you have to eat your own dog food, that is what I call it. Okay. That is the principle. Okay. You create something, you better use it before anybody will start using it. Okay. You can't, unless you are able to design systems which are bulletproof, right? You can't ask anybody else to use it. So, you have to be your own, you have to suffer all the consequences of your program not working. Okay. Another thing is that storage has to be typically persistent over time. What does it mean? It means that you write something, you expect it to be accessed later. We already discussed it some time back. We are not talking about persistence over centuries, even ability to persist over a year is some point in time. This is what I told you last time about CDs, they go bad within 1 year, right? Because I mentioned what is the reason? It is because of the dyes that are used, chemical dyes that are used, which are degrading over time, and finally you can't even read them, right? You need to get to much better dyes, then you can talk about 10 years. Series of same series can do it. Okay. And tapes, for example, they have been categorized that they will survive 50 years. That is why anybody serious about storing anything usually stores on tape. They do not even trust discs, because they do not know when it will go bad. Okay. That is the same reason why if you are, you heard all about digital effects and digital movies and everything, right? What's surprising or interesting for some of you to know is that the master copies of these things are still stored in analog form in some deep caves somewhere. Okay. They do all those things, but finally you have to keep it, because nobody knows how to, till today nobody knows how to take your bits and make it survive for 100 years, for example. Okay. They people have done some studies, they find that cost of storing it analog is fractionth of a cost of storing it digital, because digital means that you have to have a server which is running every time a new operating system comes in, every time a new disk comes in, every time a new technology comes in, you have to transfer the whole thing to that side. Somebody has to be on the job all the time watching that I have this stuff here, if I don't transfer from this side to this side, from this floppy disk to this new amazing new contraption that has come now, if I don't track the technology as it happens, okay, one day it will become bits which you can't read. Okay. So people have found that the cost of storing it unlogged is fraction of a cost of a digital system. Okay. But digital is very good from the accuracy point of view. Okay. So they want to keep both. So that's why they keep an analog must convert somehow from the digital to analog, keep that as this one, but also try to do this also, keep on transferring from one generation to next generation. It's an endless thing, you have to keep on doing it, otherwise you lose it. Okay. So amount increases typically with time, that all I think all of us are familiar with, right? You had I used to have a 64 megabyte memory stick, I thought it was big. Now I carry around 8 gigabyte of memory stick, but I'm pretty sure many of you have 64 gigabyte memory stick with you. Some of you might have 64 or 32 gigabytes. I don't have it, I'm not yet got it. So this increases with time. That means that as you keep adding more things, most of the stuff is often useless. Often that is also another fact. Okay, not important over time, something that is useful. So the trick is somehow to figure out which is the useful stuff to keep. Okay, and because of the amount is increasing, it's too difficult to even figure out what I want to keep. Okay? Sometimes people just give up; they can't figure out what is important and unimportant. Right? Same thing that happens, right? You have a lot of papers, you don't know what to throw out, what to keep. Okay. So because of this, there is an interesting thing that since not everything is important, can I keep some important part in fast storage and keep the unused part in slow storage? It's a natural thing. So concurrence is natural, keeping it in different types of storage is natural in large storage systems. That's why caching and tiering arise naturally. Okay. Caching means you keep it in faster storage. Tiering also same thing, same, but you might have in different types of storage. Okay. For example, I might say that if not everything is important over time, I will tell myself the following: I will keep it in less reliable storage, what is unimportant. I will keep it in more reliable storage, what is important. One way to do it is, I have older disks which were done in older technology, which I'm not as trusting of that. I know that it will fall apart. I will not keep most important stuff on that old disks. I keep it in the new disks. Or it could be something else also. Nowadays, you have something called solid state disks. People are not sure about how good the solid state disks are over a period of time. Or like our CDs also. Nobody knows whether it will last 1 year or 2 years. So even that it may be newer technology, but if I'm not sure about it, I want to keep my stuff in the reliable part of the storage system. So I have tiers. It could be a reliability tier based on reliability considerations. It could be performance tiers based on performance characteristics. It could also be security considerations. Okay. I can tier it at all levels or multiple levels. Okay. All these things have multiple possibilities. I can have a cross product of these possibilities. Okay. What's interesting also is that typically you have to choose between 2 out of 3 things. You can't get all 3 at the same time. If you want to get all 3, you have to spend an insane amount of money. Okay. You either decide to choose speed or capacity or cost. Okay. For example, let's take the case of speed and capacity. Okay. I can always have 10 petabytes of memory, right? It's got capacity, it's got speed, but the cost will be astronomical. I will be bankrupt. Or I can have capacity or cost. I can have easily nowadays 3 terabyte disk, cost also is cheap, but I will not get speed. I can have speed and cost, but not capacity. Okay. I can have, for example, I can even work with registers, right? CPU registers, right? I get 64 registers, fine, fantastic, extremely fast. I can access it every fraction of a nanosecond. Okay. Speed is there, cost is also, I can afford 64, but capacity is not there. Okay. I just have 64 registers of 64 bytes, 64 bits. Okay, it's trivial. So you will find that this is invariably the case: speed, capacity, or cost. Okay. There is a similar thing you can also talk about convenience and security. Okay. If you want it convenient, typically it has to be slightly relaxed with respect to security. You want to be really secure, then it has to be going to be inconvenient, like going to the airport and removing your shoes and taking your laptop, all that messy stuff, right? It's the same problem. Here also same story. Okay. If you want to keep something secure, things by definition are going to be non-so trivial. Okay. So storage performance is often the slowest storage is often the slowest component. That's why I have to do caching. Within a single device, efficiencies by merging requests. I told you that 4 kilobytes, 4 KB is too small. You want to go to larger sizes to use the bandwidth of the disks. You have to merge requests. You want to schedule requests in an order that is best with respect to device. What is called out of order execution is commonplace. You might not, requests come in, you may want to execute them, oftentimes not in the same order. It's helpful if you do it in the same order, because that's called a FIFO order, but oftentimes it turns out that you may want to do things out of order. So higher level software has to work on it. Suppose basically in some sense lower level guys will be reordering things, and the upper guy has to figure out, is it creating any complications. A good example is on a disk, for example, if there is a piece of data here and nearby there is a piece of data here, but my request requires this data plus this data here, but another request has come only for this, okay, which is near to the previous request. So should I serve this guy, go for a seek and come back here, or should I serve this guy and immediately do this guy even though this guy came later, right? So that is where the order of order execution comes in. Okay. You also have what is called okay, if a particular order required, left to user. Okay. So basically you have to tell the user you are going to suffer it if you want a particular order, because I am going to go from here, seek here, come back, go here, come back, go here. So I am just going to kill you with 15 milliseconds every single time for every 4 kilobytes. Okay. Do you want such a bad performance? If you want it, I will give it to you. Okay. Whereas if you don't tell anything, the system assumes that you are not going to tolerate such slow behavior. I will do the best in terms of out of order execution, which is good for you, okay, while keeping myself sane. For the file system, it has to have its metadata intact. Okay. So it turns out for updating its own metadata, it will actually do it in the order it is required. It won't do out of order if it is going to create problems for itself. Okay. So for sanity of the system, it might do strict order, but if it is not told anything about what you are doing, it will do what you think is good with respect to out of order. Okay. So semantically not much guaranteed, basically because it is going to do out of order if you don't tell it anything. Sometimes upper level guys, they might think something is FIFO, but actually it is getting reordered. So you have to be careful about this. Similarly, asynchronous processing is often used. For example, in Linux systems, in the recent past, not the last 5 years something, there is something called asynchronous IO framework. That means that you can initiate a request and then the kernel goes and does other things, and later when it is completed, it gets an interrupt. Okay. And basically the kernel threads are used in the kernel so that they are watching out for when the things finish, who has to process it once the particular IO is completed. Okay. So there is a lot of asynchronous aspect that goes on here. Okay. You can have parallelism across multiple devices and threads. You can have multiple heads, multiple chips. The solid state disks have multiple chips. For example, the basic size will be 8 gigabits. You put multiple 8 gigabits and all of them can be accessed at the same time. Okay. So you can have multiple heads, that means you have multiple disks. For example, you can have in high performance systems, you have something like 48 disks, 1000 disks, 8000 disks, you can have things of that kind. So all the disks are working at the same time. If you have parallel file system, it can go and try to use all the disks at the same time. It's difficult to exercise all the parallelism that's available, but that's what a parallel file system tries to do. Okay. With SSDs, people are also now beginning to figure out how to use all the concurrency that's available. Okay. So that also is another exercise. So due to slowness of devices, optimization of access is very important. What to cache, what to prefetch. Caching is demand based. Prefetch means you get it before it actually requested, so that you somehow guess when is this going to be required, when to prefetch. The big problem is usage patterns typically not known a priori. Nobody tells you what you are going to be accessing. For example, you might be using Firefox 1 minute, suddenly you start a Skype session, suddenly you want to do some terminal session or whatever, right? And it is going to have a different types of storage accesses depending on what you are doing. Okay? Nobody tells you that. You are not going to tell the operating system what's going to happen, right? It has to figure out based on your accesses. You have to figure out what you are doing. Okay? So that's why there's a big difference in performance whether sequential access or random. I already mentioned to you, if you keep pulling out 4 kilobytes followed by seek, your performance really is going to be pitiful. Okay? So if it is sequential, somehow you can guarantee it is sequential, then it is much better. So whole operating system and storage system, they sit and figure out how to make sure that you are pulling out hundreds of blocks in one shot. Okay? It's a very big issue in operating system design / storage system design. Okay? Again, similar to that, if you are doing tiering, system is slow if too many on demand migrations from slow to fast tier of storage. There are too many latency delays. Okay? Often optimizations, critical and override semantics. I already mentioned this, out of order processing typical. That's why you have complex higher level software. Okay? And for the same reason why databases and file systems are slightly complex things. They are not that simple to design. Once it is designed, people don't tend to change it. Okay? So typically because of the complexity, simple and robust methods are useful, because there is a certain let's say, just avoid the complexity, you find that this is something useful. Okay? So okay, I think we'll just mention a few things about protocols. Already I mentioned that there could be protocols at the device level, it could be at the other levels of the stack, like for example at the intermediate levels or at the top levels. Okay? So, for example, you typically storage protocols, you are interrupt driven rather than wait pole. On completion interrupt the CPU or a CPU's agent. A CPU's agent is typically in storage system called host bus adapter. Okay? A host bus adapter is an agent of the CPU, which instead of CPU wait, let's say processing the interrupts, the HBA does it. For example, let's say the CPU wants a buffer of 16 kilobytes. Then without a HBA, the CPU will interrupt it 4 times for every 4 kilobyte transfer. Okay. So to avoid the CPU getting interrupted so often, they have host bus adapter, which is another small little system of its own. It's another CPU, you might call it some kind of a small system. The disk subsystem will interrupt the HBA. HBA will take each of those 4 blocks that have been read, put them together, what is called reassembly. Okay? In networking, you might have heard of something called segmentation and reassembly, SAR, right? So the HBA basically does the SAR for storage devices. Okay? Okay? So you have HBA or similar agents, helps segmentation reassembly. HBAs do other things also. We will not get into it, but one of the things it does is this. Okay. What is called split phase transactions are also common. What are split phase transactions? Instead of doing, I sent something, you respond back, right? You send something and you essentially opt the transaction for some time, and later, sometime later, again you initiate this transaction. Okay. It's not as if when I send it, I am waiting for the other guy to respond. Okay. I send it, I do other things, I just completely lose track of the beginning part of it. Okay, I just go and do other things. Sometime later, I will be told that you didn't complete transaction, you better finish it now. Okay. On completion of a long seek, slave takes the bus. Okay. Other interesting thing about storage protocols is protocol endpoint preferably virtualizable. What does that mean? Okay. You can see the explosive size of disk systems. When I first started teaching in this institute, the size of disk was what we talked was 4 megabytes. I remember in 1995 or 96, I bought the biggest disk that was available cheap. Okay, that was 495 megabytes. Okay, 495 megabytes. Okay, now think about it. 495 megabytes, how much? It's close to a gigabit. That's about 31 bits. If you want to refer to each bit, you require 31 bits or 30 bits or whatever. Right? Now, 32 bits is not enough. You have to go to 64 bits. That means that everything in the system is changing with respect to sizes. Beginning you start with 16 bits, that's not enough. You went to 32 bits, that's not enough. Now we went to 48 bits, probably we got 64 bits also. Okay. Now what it means is that if you have any specificity with respect to each of those endpoints, what this guy requires, what that guy requires, you get into problem. That you can also see in the case of 2 terabytes and 3 terabytes. Between 2 terabytes and 3 terabytes, there is a problem. Okay. There is some size limit that is coming in the BIOS somewhere, or in some lower level part of the subsystem. That's why we will find that 2 terabytes are acceptable in some systems without trouble. The minute you put a 3 terabyte system, that guy can't recognize the 3 terabytes, it will give you some, it will only give you some 900 gigabytes, something like that. Okay. Because it is chopping off, it is doing some truncating of the higher bit, something of that kind. Okay. So what is important is that since evolution of these devices are taking place all the time, you want it to be what is called virtualizable. That means that you don't want it to be a hard, let us say, numbers which are fixed once for all. You want to be able to do something which, depending on the situation, you can change certain things. Okay. So, for example, SCSI devices, right? Originally they started an electrical bus, now they are networkable. You have something called SAS devices, SCSI based storage systems. Okay. Nowadays you can even access a disk through internet. There is something called iSCSI. There is a disk sitting out there. I can send commands through internet to talk to that disk. That is called iSCSI. So now the thing is, it could be electrical bus, it could be network, etc. So what's important is that somehow you want to make sure that the aspect relating to storage and access, that should be independent of which way I actually access it, whether I'm accessing the electrical bus, network, etc. In a sense, that's what I mean by saying it has virtualizable. It should be designed in such a way, in a client server kind of model, let's call it client server model, which somehow abstracts away from these issues. If you are able to do a successful abstraction, the same SCSI protocols will keep living on. For example, the SCSI devices came in 1980, it came in 82, 83, somewhere about that time. Some new versions came out. The SCSI 2 came in about, I think, mid 90s. SCSI 3 came in early 2000. And in spite of all these changes, in spite of the speed changes, in spite of all those things, in terms of the SCSI protocol has not changed, mostly. Minor additions have been made here and there. Okay, because it is robust with respect to changes in the device space. Okay, that's one of the things that are, okay. Devices can have arbitrary structure as long as they speak SCSI protocol. Actually, what's interesting is that you will find that if you talk to a big storage systems, a big server with hundreds of disks and multiple servers, means tens of servers, disks, etc., they will all present itself as a SCSI device to the rest of the system. Okay, all of the stuff will be speaking the SCSI protocol. So a SCSI, any kernel system knows about SCSI. Okay, they will give you SCSI commands, and this system is to understand what this SCSI command is. It does some processing and finally pretends as if it is SCSI device and sends back. Okay. So I'd like to conclude. Storage system design has many ramifications of the rest of the system. We want to provide abstractions based on application needs and devices. Design needs to be sensitive to cost, device and manageability. Okay. It also introduces new abstractions with time. We will talk about this soon. For example, key value stores an example. A good example of this is the Cassandra file system from I shouldn't say file system, Cassandra system from Facebook. Okay. That's a key value store. Okay. It's not a file system kind of model, it's a slightly different model. Okay. and you need to scale to support large scale computing systems. This has to scale like anything, because the storage, what you are storing and what you are retrieving also become bigger and bigger. Okay. So these are some critical things. That is the reason why nowadays storage systems are becoming critical parts of computing infrastructure, and there are completely new designs, completely new ways of looking at these things, and that is what we will be looking at this course. Okay. So, we will next class we will start looking at some very simple storage systems to slightly more coming in some detail, so that you get an idea. Okay.